Continuation to the next question. Question number 19 says from figure 19.1 shows the image from an experiment using a ripple tank. So we can see the image of an experiment using a ripple tank, and the question reads, a straight ruler repeatedly hits the surface of water. Waves on the surface of the water travel in the direction shown by two large upward white arrows. The waves are incident at a solid barrier. Okay, closely examine the image in figure 19.1. State two-wave phenomena, two-wave property that can be observed in this image. You may annotate figure 19.1 to support your answer. So the two phenomena or properties are, we have reflection, because we can see the wave in the water, so there can be reflection once it hits the barrier, the solid barrier. And two is diffraction. Okay, the water can also be diffracted, as you can see it spreading out. The spreading a wave when it encounters an obstacle, that is what we refer to as refraction. Now, the B part of the question says two transmitter A and B emit coherent microwave in all directions. A receiver is moved at constant speed along the line from P to Q, which is parallel to the line joining the two transmitters, as shown in figure 19.2. Okay, figure 19.2 is shown, as we can see up there. So now, having said that, the question now is this: explain why the output signal from the receiver fluctuates between maximum and minimum values as the receiver moves from P to Q. Now, what we want to explain here is interference of wave. So, interference of waves, which can be constructive and also be destructive. Now, at the point of the maximum fluctuations, we have the constructive interference. However, at the minimum, fluctuation we have the destructive interference. Okay, So that explains that. Now the next question says, an approximate value of Planck constant H can be determined in the laboratory using the light emitting diode LED. An LED suddenly starts to conduct and emit monochromatic light when the potential difference across the LED exceeds a minimum value V0. The potential difference V0 and the wavelength of the emitted light are related by the equation V naught equal Hc over E multiplied by 1 all over lambda, where E is the elementary charge and C is the speed of light in vacuum. Figure 20.1 shows some data points plotted by a student on a V naught against 1 over V graph for 5 different LEDs. Okay, we have seen the grid. The potential difference across the LED was measured using a digital voltmeter with dimension plus or minus 0.001. The value of the wavelengths are accurate and were provided by the manufacturer of the LEDs. The value of the V0 determined by directly observing the state of the LED in the brightly light laboratory. As to draw the straight line of best fit on figure 20.1 and determine the gradient of the slope. So first we draw the straight line of best fit, okay, which possibly will not pass through the zero origin. Let's see if that works. No. Okay, we have one that works. So now we are asked to determine the slope. So how do we determine the slope? So we are asked to determine the gradient. Gradient is the same as the slope. So we find a place of best fit, can let our slope, our gradient be as big as possible. So if we trace it from somewhere here, excuse me, we use this, again we use this, we can trace this out to be 2.5. if this is 2 and this is 3, this is 0, this will be 0.5, and we have the slope somewhere around here, which is 0.4. And then we trace this. This is 1.0 for the y-axis. And then if this is 3 and this is 4, we have this part 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.6. So our slope is going to be 3.6. Our gradient is going to be 3.6 minus 1.0 and divided by 2.5 minus 0.4. So 3.6 minus 1.0, that gives 2.6, and then 2.5 minus 0.4, that is 2.1. Don't forget, this is 10 to the power of minus 6 times 10 to the power of 6 rather. So it's going to go up, and once it attains the upper part, we have 2.6 divided by 2.1 times 10 to the power of negative 6. Okay, so what do we have? 2.6 divided by 2.1, that is 1.23, times 10 to the power of minus 6. Okay, so there we got the potential difference. We got the gradient. So we have to use the answer in Roman figure 1 and the equation on page 20 to determine the value of the h, which is the Planck constant, to choose SF, two significant figure, and show your workings. So the equation in page 20 is V equal to, that is V naught equal to HC over E. V naught equal to HC over E multiplied by 1 all over lambda. So V naught, we want to use that to determine H. Okay, do we have the value for the V naught with respect to the question? So our V naught, H is the Planck constant, C is the speed of light, and then E is the charge, Y we have the lambda, which represents the wavelength. Okay, so this, when we compare this with the equation of a linear graph, so this happens to be our gradient. Okay, so this is our gradient. When we compare this, y equals mx. The y-axis we plotted this, the x-axis we plotted 1 over lambda. So our gradient, okay, our gradient therefore is equal to hc over E. So we calculated gradient to be 1.23 times 10 to the power of minus 6. 1.23 times 10 to the power of minus 6 equal to h times 3 times 10 to the power of 8 all over 1.69 times 10 to 1.6 rather times 10 to the power of minus 19. All right, so on cross multiplication, h therefore will be equal to 1.23 times 10 to the power of negative 6 times 1.69, 1.6 times 10 to the power of negative 19 divided by 3 times 10 to the power of 8. All right, so 3 times 10 to the power of 8 is going up to be 10 to the power of minus 8. So that is gone. So we have 1.23 multiplied by 1.23 multiplied by 1.6 divided by 3. Okay. So what does that gives? That's 0.66 times 10 to the power of 6 minus 19, that is minus 25. Minus 25, that is minus 30. Minus 25 minus 8. So that's going to be minus 33. All right. So to 2SF, that would be 6.6 times 10 to the power of minus 34. Okay, so that's the value of the Planck constant calculated. And they said we should calculate the percentage, calculate the percentage difference between your value in Roman figure 2 and the accepted value of the Planck constants. Okay, so the value we got here is 6.6 times 10 to the power of minus 34 minus the standard 6.63 times 10 to the power of minus 34, okay, divided by 6.63 times 10 to the power of minus 34 multiplied by 100. Okay, so 6.63, 6.6 minus 6.63, okay, so we have 0.03 6.63 times 100 over 1. So 0.4%. So we are asked to identify two types of error shown by the data in okay, identify two types of error shown by the data in figure 20.1 and suggest how you could have refined experiment to reduce or eliminate this. Okay, we have the random error, because the points on the grid are spread about the line. There is also systematic error, because line does not pass through the origin. Experiment can also be conducted in a dark room. In a dark room